fourth colligative property is osmotic pressure, symbol is pi. We all know the process called osmosis. It is the movement of the solvent molecules from their region of higher concentration towards lower concentration across semi-permeable membrane. All bio students are very familiar with this very famous process, which actually is the basic of the biological system or of the living beings. That what we notice in this case is that whenever a solution is separated from the pure solvent by a semi-permeable membrane, the membrane which is actually is like a normal your animal membrane, or plasma membrane, or you can say a normal cellophane sheet like this. What happens is the pure solvents start moving from its region of higher concentration towards the solution side, which is having a lower concentration of the solvent. And this movement takes place through the small pores which are there in these semi-permeable membranes, through which only the solvent molecules is allowed to pass through. These small pores are so small that the solute cannot pass through them, so it only allows the movement of the solvent molecules across them. So what happens is the solvent molecules start passing through it. And this concentration gradient results in the movement of the water molecules, and this water molecules movement is called osmosis. Like we can see, we have taken in a thistle funnel, a semi-permeable membrane has been tied on its mouth, and a sugar solution has been taken into it, and the inverted funnel has been hanged in the pure water. Now water concentration is higher outside and it is very less inside, because inside we have a sugar solution. So solvents start moving from outside towards inside. See, it's not like this that the solvent is not coming out also from inside towards outside. It's also coming out. But the rate with which the water is going inside to this along the concentration gradient is much faster or is much higher. Therefore, what we find is that the sugar solutions levels start increasing, because this entering of the water into this is forcing this solution to expand or to increase in its volume. So the pressure which this solution, the moment they enters into the solution side, the solvent molecules are putting up is resulting in the increase in the sugar solution level. It goes to a height of h, and we can find out this the pressure exerted by this with the formula rho g h, which is called your osmotic pressure. So what is osmotic pressure is? Suppose we want to stop this entering of the solvent molecules to this thistle funnel. We'll put certain pressure on this thistle funnel from this side, so that we can stop the entry of this solvent molecules into the thistle funnel. So the pressure applied to stop osmosis is called osmotic pressure. So the pressure applied to stop osmosis is called osmotic pressure. This is most important. Now, which is given a symbol pi. And we can find out the value of this pi by the height of the column which has, or the sugar solution which has attained with this, the height which this sugar solution has attained from the formula rho GH. There are many other apparatus like Barclay and Hartley apparatus which are used to find out the osmotic pressure, and this osmotic pressure gives a very valuable information regarding the concentration of the solution, because actually it is the movement of the solvent molecules along the concentration gradient. Now experimentally it was found that this pi, experimentally it was found that this pi is proportional to C. What is C is? The C is the concentration of solute in solution expressed in molarity, moles per liter. And remember, this is a universal thing, that whenever in the osmotic pressure numericals or in the data, if the concentration is expressed in terms of percentage, it will be always mass by volume, because we have to use concentration in terms of the molarity. Now as we know, the pi is proportional to C, there is one more factor on which the pi, the osmotic pressure, depends, and that is the temperature at which the whole of this process is taking place. Because higher is the temperature, higher will be the kinetic energy of the molecules, so higher will be the rate with which they will be moving along the concentration gradient. So more of the pressure is applied towards this solution side. So higher will be the pi. So pi is proportional to C, pi is proportional to T. So what we can make out is pi is proportional to Ct, and this proportionality is opened by a constant which is called CRT. This is CRT. So the formula of finding out the pi is CRT, where R is the same gas constant whose values will be 0.0821 liter atmosphere per Kelvin per mole if we are taking the pi, or we are finding out pi in terms of ATM, and if it is in terms of bar, it will be 0.083 and so on. So the R is the same gas constant, C is the concentration, and T is the time or temperature, and we can write down this formula in one more way, and that way is that we can expand the C as weight of the solute, molar mass of the solute, 1000 upon B, because this is how we can find out molarity, into R into T, and this is how we can find out the exact pi. The osmotic pressure of any which develops in any solution due to its separation from its pure solvent through the semi-permeable membrane. This is what is phi is, and this formula can be used to find out the molar mass of the solute present in the solution, as it is the colligative property. Also remember one most important thing. This osmotic pressure, out of the 4 colligative property formulas or 4 colligative properties, this property or this method is the best method of finding out the molecular masses of the solutes, especially when the solutes are polymers or are the solutes whose molar masses are very large. They are in 10,000s or in thousands, and we know because larger is the molar masses, we know, or they all are in denominators, smaller will be the values of these colligative properties. So if larger is your solute, smaller is the colligative properties value. But in case of osmotic pressure, the advantage is, since no heating or the cooling of the solution is required, no temperature variation is required, we can easily, there is no danger of the decomposition of the solute, plus the magnitude, even if the molar masses are very large, like in case of polymers, will be large enough to be determined very accurately, because in ATM it means what, we can change it into what in mm, so which can be determined very easily. Another advantage is that a very small amount of even the solute can create a concentration gradient through which we can find out pi. Another thing is that we can recover the solute. So all these properties, all these benefits together make this method as one of the most popular and important method of finding out the molar masses of the solutes, specifically when the solutes are polymers or are the substances which are having very large molecular masses. Before moving into the numericals of the osmotic pressure, one must understand certain terms which are used in this case. Like if suppose we want to see an animal cell live under the microscope, we know that these cells are having large organelles called vacuoles, in which they have what, cell sap, which is the water, is the water along with some electrolytes or ions dissolved in it are present inside this. These cell vacuoles keeps the cell in the proper shape, and the solutions present in them are called cell sap. Now if you want to see this like our RBCs or any other animal cell live under the microscope, we have to take this cell in a solution. Now the solutions therefore which are taken can be of 3 types. They can be isotonic solutions, hypertonic solutions, and they can be hypotonic solutions. So let us see first isotonic. As the name indicates, iso means same, tonic means concentration. When the outside solution's concentration is equal to the cell sap's concentration, or if the 2 solutions are having the same concentrations, we say that both the solutions are isotonic solutions to each other. And in this case, remember, once we say isotonic, the pi of one of the solutions will be equal to the pi of the other. That means the osmotic pressure created in one of these solutions will be equal to the osmotic pressure created due to the other one in the other solution. So their pi's will be same. Like if we want to see our RBCs live under the microscope, we know that we have to take them under in 0.9% by percent weight by volume solution of NaCl. Then only we can see them live without any change in their shape, because what happens is then that the rate with which water is entering into the cell is equal to the rate with which the water is coming out of the cell. So cell remains in its original shape without any change. So these are called isotonic solutions. Suppose we take the same RBCs in a solution which are having higher concentration than the cell sap's concentration. So it means if the concentration is higher than 0.9 per weight by volume percent, of course, then what we find is that the solution is more concentrated than the cell sap. So more of the solvent is present inside the cell than the outside. So water starts coming out of the cell. This results in the hypertonic solutions results in shrinking of the cells. Shrinking of the cells, which is also called plasmolysis. Shrinking of the cells or plasmolysis. This is what is called. And this happens when we place these cells in the hypertonic solution, the solution which are having higher concentration. The water starts coming out of these cells. Now, the third case, hypotonic solutions. As the name indicates, hypo means lower, tonic means concentration. If suppose we place the cell in the solution whose concentration is less than the 0.9% weight by volume, what we find is more of the water is there outside the solution, or in the solution which is lying outside than the cell sap. So water starts actually entering into the solution. So the cell starts swelling. The swelling of the solution, the cell takes place. Swelling of the cell takes place, which is called edema. This is also called edema, and the cell there can a stage can come where the cell will burst ultimately, because the water keep on entering into this until the concentration of both the solutions becomes equal, and by that time the pressure becomes so large that it bursts. So the hypertonic solutions are the one which are having a lower concentration. So 0.9% weight by volume solutions concentration is less than this, we find that the cell bursts. So these are the type of solutions which we must know before proceeding into the numericals of the osmotic pressure. Let us see how the osmotic pressure is used to find out the molar masses of the solutes or the osmotic pressure of the solutions. The numerical is calculate the osmotic pressure of 36% by volume glucose aqueous solution at 300 Kelvin. So we are given temperature 300 Kelvin. The solute is your glucose, so its molar mass will be 180 grams per mole because it is C6H12O6. Then it is 36% by volume means what? Your weight of your solute is 36 grams. And volume of the solution will be 100 ml because it will be 36 grams of the glucose in 100 ml of the solution. So it's 100 ml. So now we can, and we already know R will be 0.0821 liter atmosphere per Kelvin per mole. So pi will be weight of the solute, molar mass of the solute, 1000 by V, R into T. So it will be 36 by 180 into 1000 by 100 into 0.0821 into 300. So it will be 10, it will be 0.2. So it will be somehow 0.2 into, it will come out to be 24.63, which is 49.26 atm. So this is what is the pressure we have, 49.26 atm when 36% of the glucose solution is taken in 100 ml of the in a solution is taken, or 36 grams of the glucose is taken in 100 ml of the solution at 300 Kelvin. Let us see one more numerical on the osmotic pressure. It says find the molar mass of a non-volatile solute whose 10% by volume aqueous solution is isotonic to 3% by volume urea aqueous solution at 300 Kelvin. It means what? Like in a beaker, when we separate it, divide it into its two part by semi-permeable membrane. What we have is on one side we have an unknown solute X, and on the other side we have a urea solution. X solution, which is unknown, is 10% by weight by volume, and this is 3% weight by volume. The question is that we have to find out the molar mass of this one. So it means what? That the weight of the X unknown solute is 10 grams. Its molar mass we have to find out. The weight of the urea is 3 grams, and its molar mass of urea is, we already know, it's 60 grams per mole because it is NH2CO NH2. And temperature we know is 300 Kelvin. It's same for both the sides. So what we know, since the solutions are isotonic solutions, as I have told you, the pi due to X will be equal to pi due to urea. The pi of both these solutions will be same. Now let us put the values into this simple comparison. What we have is, if pi of the unknown due to the unknown solution is equal to the pi due to the urea solution, we can write concentration of due to the concentration of the unknown solution, which is 10%, RT into the concentration of the urea solution into RT. Since R and T will be same in both these cases, it gets cancelled. So it is the comparison of the concentration of the unknown solution and the urea solution. Concentration will be in terms of molarity, so it will be what? Weight of the unknown solute, molar mass of the unknown solute, 1000 into what is, how much is V? It will be equal to weight of the urea, molar mass of the urea, 1000 upon V again. So it will be your this expression. Now we know the values of these notations. The weight of the unknown solute is 10 and its molar mass is not known to us. This 1000 upon V, 1000 upon V is the same because volume is 100. It will be same because both are in percentage, so it will be 100. So what we are left with 10 upon mx, and it is 3 upon 60. So it's 20. So mx therefore is found to be 200 grams per mole. So this is what is the answer is, and this is how we can use the colligative property osmotic pressure to find out the molar masses of the non-volatile solutes present in the solution. Abnormal molar masses. See, the main idea of studying the four colligative properties is to find out the molar masses of these non-volatile solutes which are added into these liquid solutions. Now, these are the four formulas of the four colligative properties which I have written. And the left hand side of these four formulas are the colligative properties. This is RLVP, elevation in boiling point, depression in freezing point, and osmotic pressure. And the main idea of studying these four properties is to find out the molar masses MB. So from these formulas, we can easily make out two very simple things. Like the colligative property is directly proportional to the number of the moles of the solute which is present in the solution, as well as the colligative property is inversely proportional to the molar mass of the solute which is there in the solution. So larger is the mass, lesser will be the value of the colligative properties. So that is why if I compare, I'm having 1 gram of urea and I'm having 1 gram of glucose, and I compare and dissolve them in the same amount of the water. What I can say is that if I take this urea and if I take this glucose solutions, what I find is that the boiling point of this urea solution will be more than that of the glucose solution because it has a molar mass of only 60, whereas it has a molar mass of 180. So this is how we can do certain comparisons. And the basic purpose is to find out the molar masses of the solutes. But experimentally we came across many solutes whose molar masses when determined by these colligative properties were found to be coming out to be different from their theoretical values. Like I can show you the examples, like suppose NaCl, when NaCl's molar mass was determined, was experimentally found, it was found to be experimental molar mass was found to be actually coming out to be 29, whereas its theoretical molar mass we all know is 58.5. Then another example is acetic acid. Its experimental molar mass was found to be 120, whereas its theoretical molar mass is 60. So this is how, these are certain examples these I have given you. Otherwise there were lots and lots of examples of the solutes whose molar masses when determined by these colligative properties were found to be different from their theoretical values. Now such solutes whose molar masses are coming out to be different from their theoretical values are called abnormal molar mass showing solutes. And these 29 and 120 experimental molar masses are called abnormal molar masses because they are abnormal, they are different from the theoretical values. Initially it was thought that there is something wrong with these formulas, but we know these are the formulas based on the fundamental basic properties of the solution, they cannot be wrong. So then Wendhoff studied this actually in detail and he came out with the explanation. So Wendhoff studied this problem of the abnormal molar mass in detail and he came out with the explanation that the reason of these abnormal molar masses are the nature of the solutes. What happens is when the solutes are added to the solution, they either dissociates or associates. Now in both these cases their experimental number of moles gets changed. Once their experimental number of moles gets changed, their colligative properties get changed and therefore their molar masses when determined experimentally were found to be different from their theoretical values. Let us see this actually more clearly with the examples. Let us take first the example of the dissociation. I will write down here that this is directly proportional to the molar mass and inversely proportional to the molecular mass of the solute. Now let us take the example of dissociation. Now let us take a solute AB or a salt AB which when added to water forms A plus and B minus. Now we know that it's 1 mole on dissociation gives you 2 moles. Let these are n moles. Once we get n moles, so you can clearly make out that now the number of moles experimental are n times of the one which we assumed. So once the number of moles are n times, the colligative property will also become n times and the molar mass becomes divided by n times. So what we get is therefore the experimental colligative property will be n times of the theoretical colligative property and the same experimental molar mass will be what? Theoretical molar mass by n time. Like we can take the example of NaCl. In case of NaCl, their experimental colligative property becomes double, but the theoretical molecular mass is divided by 2, so it becomes what? 58 divided by 2, that is why it was coming out to be around what? 29. So this is how the experimental molar masses were coming out to be different. Now in order to solve this problem, Wendhoff introduced a factor which is called Wendhoff's factor, which is called I. Now he said this I is basically is theoretical molar mass upon experimental molar mass, or it can be experimental colligative property upon theoretical colligative property. He said we can find out the value of I by this formula, and as indicated the I, basically what he said that this I will be equal to n for 100% dissociation. Therefore, the I for NaCl will be equal to 2, for AlCl3 solute it will be 4, for MgSO4 it will be 2, and for K4FeCN6 like solutes which are actually complexes, it will be 5 because 1 this complex and 4 potassium. So he said once we know the I, he said what is to be done is, he said that simply multiply the right hand side values of these formulas with I. What he said that once these are right hand side are multiplied by I, using the same formula we can get the exact correct value. Like suppose in case of sodium chloride, the MB theoretic experimental was coming out to be 29. I for NaCl is 2. So when 29 is multiplied by 2, you get 58. So approximately the answer is correct. So he said once we multiply this I with these formulas, what we get is we get the correct answer. And this is what his explanation is. He also said that if the solute is not showing 100% dissociation, suppose the solute is not showing, if dissociation is not 100%, alpha, which is we call it degree of dissociation, is involved. What he said that if this AB gives you A plus and B minus, we have 1 mole of this, and 1 minus alpha is formed, alpha of this and alpha of this is formed, or we can have in total n alpha moles of the salt or ions are formed. The total moles will be how much? How many? 1 minus alpha plus n alpha. So he said this I since is equal to experimental number of moles upon theoretical number of moles, because experimental colligative property upon theoretical colligative property, and colligative property is directly proportional to number of moles. So experimental colligative property can be written as experimental number of moles. Theoretical colligative property can be written as theoretical number of moles. So it is 1 minus alpha plus n alpha upon 1. So what we get is that once the dissociation is not 100%, the I will be equal to 1 minus alpha plus n alpha. And this formula can be used to find out what the alpha degree of dissociation of any solute experimentally, which is not dissociating completely. So this is how he explained. Now we can take the examples of the association, but before this we need to understand all salts, all carboxylic acids, phenol, all of these types of solutes when taken in the polar solvents shows dissociation, and their I will be always more than 1 because experimentally the number of moles are getting increased. Now let us see dissociation. Association. Now let us see how the molecules gets or the solute gets associated. We can take the example of acetic acid. When this is taken in benzene or in any other non-polar solvent, what we find is its two molecules forms a dimer like this. So they forms dimer. So if we have 1 mole of this acetic acid in solution, actually it becomes half mole. Since the number of moles experimental become half, we can make out the colligative property will also become half, but the molar mass will become double. And that is why in place of 60, its experimental molar mass was coming out to be 120. Now, how the Wentoff rectified it? Wentoff said the I for such cases will be equal to 1 by n, where n is the number of molecules associating. So in case of dimer, remember I will be 1 by 2. In case of trimer, it will be 1 by 3. And in case of tetramer formed, it will be 1 by 4. So this is how the I gets changed. And what we find is, since the number of moles of the solute are getting decreased, in this association always I is less than 1. So we cannot put the I as 1, it will be less than 1. And it depends that how many mole molecules of the solute are associating. Now the value of the I's will be taken as this if the association is 100%. and therefore we can make out like experimental molar mass of the acetic acid was coming out to be 1 by 120, and its I will be, since it forms a dimer, is 1 by 2. So 120 into 1 by 2 will make it 60. So by using these formulas, yes, we can find out the exact molar mass. So Van 't Hoff solved this problem, and according to this Van 't Hoff, this I will be taken as equal to 1 by n in case the association is 100%. Now if the association is not 100%, we can make out like this. If we have taken 1 mole of this and alpha moles of this associates, the moles of the product formed are alpha by n, because n is the number of moles associating. So the total moles will be 1 minus alpha plus alpha by n. So I, as I have told you, is your experimental number of moles upon theoretical number of moles, 1 minus alpha upon alpha by n upon 1. So your I is equal to 1 minus alpha plus alpha by n. So this is what is the formula is if the solute taken is not showing 100% association. So this is how we can find out the molar masses of even the solutes which are actually undergoing association in the proper way. Another important thing, what all are the solutes which shows association? Carboxylic acids like benzoic acid, like acetic acid, phenol, etc. When taken in the non-polar solvents in place of dissociation, they shows association, and their alpha I is found to be less than 1, and we can find out their alpha or degree of association also. Now let us see how the Van 't Hoff is used in the numericals. Like find I for K3FeCN6, which is called potassium ferricyanide, which shows 60% dissociation. See, if this was not given, we could have taken the I for K3FeCN6 as 4, 1 complex, and this 3 potassium. But since it's not showing 100% dissociation, we can't take its I as 4. It will be less than 4, but definitely more than 1. And what will be the exact value? Let us see. We know the formula is I is equal to 1 minus alpha plus n alpha in case of dissociation, when the dissociation is not 100%. Alpha given is 60%, so out of 1 it will be 0.6. And the n number of moles, the ions formed on dissociation by this are 4. So I will be equal to 1 minus 0.6 plus 4 into 0.6. So it will be 0.6 plus 2.4. So it will be 3. So in place of 4, we cannot take 4, it will be 3. So this is how the I gets changed the moment we have what the degree of dissociation or degree of association are not 100%. Let us see another numerical, how the information of the Van 't Hoff factor can be used to find out the colligative properties. See, it says find osmotic pressure of 20.6% of volume by volume NaBr solution which shows 90% dissociation at 300 Kelvin. So we have to find out pi. We know the formula will be pi ICRT. Don't forget to write down I. In fact, you have to remember that always the I is there in these colligative property formula. And in case of dissociation, it is more than 1. In case of association, it is less than 1. And it is equal to 1 when the solutes are non-volatile, like we can have urea, glucose, sucrose, fructose, glycol, like this one, glycerol, etc. So in these cases, I is always 1. Now, and like in this case, we know sodium bromide is a salt. Now its I we cannot take as 2 because it will give us 1 sodium and 1 bromide, because what happens is the dissociation is not 100%. The dissociation is 90%, which is out of 1 will be 0.9. N is 2. So first we have to find out its I, which will be 1 minus alpha plus n alpha, which will be 1 minus 0.9 plus 2 into 0.9. So it will be 1.9. So in place of 2, we will take its I as 1.9. We already know R will be equal to 0.0821 liter atmosphere per Kelvin per mole. And we already know the weight of the solute will be 20.6 grams, volume will be 100 ml, and the molar mass of the sodium bromide is 80 plus 23 is 103. So what we can make out is pi will be equal to 1.9, it will be 20.6 upon 103 into 1000 upon 100 into 0.0821 into this we can rub out actually, because this we already know now. So it will be 300. So this comes out to be 10, this comes out to be 0.2, so it will be 1.9 into 2 into 24.63. On multiplication we get 93.594 atm. So this is what is the atmospheric pressure of 20.6% by volume NaBr solution at 300 Kelvin.